This can be produced via a named reaction called the Grignard reaction, which starts from an alkyl halide and produces an alcohol and the reaction involves magnesium metal. Magnesium will insert between a carbon halogen bond to form what is known as the Grignard reagent. The Grignard reagent is then treated with an aldehyde, ketone, or ester to form the alcohol product. And if we look at the scope of the reaction, we can see that aryl groups and alkyl groups are both possible to use in the Grignard reaction to form the Grignard reagent. So these are examples of Grignard reagents that you can form. The reaction is very general. Essentially any type of alkyl halide will do. Iodine is the best halide to use, but also bromine and chlorine are acceptable as well. The Grignard reagent can be shown as a bond between carbon and magnesium that is polar covalent or ionic. And that's because there's a difference in electronegativity between carbon and magnesium of about 1.2. And that's technically polar covalent, but it has a lot of ionic character. So the bottom line is this particular carbon has a lot of negative charge. Whether or not it's a full negative charge or a partial negative charge, it still has a lot of negative charge. And so essentially it's like a carbon anion, and as a result will function as a strong nucleophile as well as a strong base. It's difficult to form a carbon that's anionic in any other way, because typically sp3 hybridized hydrogens attached to a carbon like that are not very acidic. So there would require an extremely strong base to deprotonate a hydrogen attached to an sp3 hybridized carbon, and it would need to be a very, very strong base, because the pKa of this type of proton is approximately 50, which means it's the weakest acid you can possibly have. So essentially there is no base that's really strong enough to deprotonate. So if we're able to form the equivalent of a carb anion via formation of a Grignard reagent, then that will have a lot of synthetic utility as a strong nucleophile, a carbon-based strong nucleophile / strong base. Okay, so what sort of scope of reactions are we looking at? This is an example of a ketone, right, being attacked by a Grignard reagent, and the product is a secondary alcohol. The proton comes from the water workup at the end. And notice we formed a new carbon-carbon bond, which is highly sought after by organic chemists to be able to increase molecular complexity. Another example would be if you had started with an aldehyde and treated that with a Grignard reagent, keeping this very generic RMGX water. We could form a new carbon-carbon bond. Excuse me, up here this was a tertiary alcohol, and this is a secondary alcohol. So ketones form tertiary alcohols, and aldehydes form secondary alcohols. Remember, we talked about the Grignard reagent is both a strong base and a strong nucleophile. We want it to behave as a strong nucleophile to attack the carbonyl carbon of an aldehyde or ketone. But it's possible it could act as a base if there was an acidic proton nearby, which is why as soon as we form a Grignard reagent, for example, phenyl magnesium bromide, we would want to take care to avoid exposure to anything acidic, such as even water, which is not a super strong acid. It would definitely be strong enough to protonate a Grignard reagent. And if that happens, we transfer a proton, and the resulting product of that would be benzene and hydroxide. So typically we're not looking to form a Grignard reagent just to protonate it, right? So this is sort of a side reaction that we want to avoid. So in order to avoid that, we would want to pay careful attention to excluding water from the reaction. So as a result, we're definitely not going to use water or any type of polar protic solvent such as methanol or ethanol as the reaction solvent. Instead, typically we would use anhydrous ethers as the solvent. So anhydrous means rigorously purified of water, so there's no water around, right? So common solvents are ethers such as diethyl ether. This works really well because the negatively charged oxygen or partially negatively charged oxygen will coordinate to the magnesium ion in solution that's formed as a result of formation of the Grignard reagent. And it helps stabilize the Grignard reagent. So here are some examples. This is cyclohexanone, which is a ketone, being treated with, in this case, a methyl magnesium bromide. And you can see that the methyl group has been incorporated with the new carbon-carbon bond. So overall, you can think of it as very generically a ketone forming a tertiary alcohol. And this is an example of an aldehyde being reacted with the same Grignard, in this case methyl magnesium bromide, and the product is a secondary alcohol. Notice that we did form a stereocenter, and it mentions that a racemic product is produced because there's no preference for the Grignard reagent to attack the planar sp2 hybridized carbon from the top or the back face. So it'll do both in equal amounts, producing a racemic mixture. This is an example of an ester being reacted with a Grignard reagent. Notice it mentions excess of the methyl magnesium bromide, and that's because we will need at least 2 equivalents in order to get a good yield of the product. And so we have incorporation of 2 methyl groups and the formation of 2 new carbon-carbon bonds in this particular case. So in all 3 of these examples, they did use methyl magnesium bromide, but just note that it doesn't have to be a methyl group. It could be any alkyl group, because really there's lots of versatility in the type of alkyl halides that can be used to form the Grignard reagent. Remember, R can be an aromatic ring, a vinyl group, an alkyl group, and if it's alkyl, it could be primary, secondary, tertiary. There's very little limitation to what it can be. The only limitation really is there can be no acidic functional groups present.